Good morning. How does who can tell me the steps for the page fault handler? I'll start with you near the window there. Page fault handler. What does it do? If we need a page, okay, before you answer your question, I'll get to another question here. What's meant by a page fault? What's a page fault?
When the page is requested by the memory,
when the page is requested, not necessarily by the CPU, just requested by another page, and during execution, and it's not located in main memory. We call that a page fault. And what's thrashing? Thrashing? Yeah? It's excessive page faults, very frequent page fault. And what's wrong with thrashing? What's wrong with thrashing? What's the problem with thrashing? We know what it is, right? You know what thrashing is? Okay, he's going to tell you what thrashing is. Tell him.
Thrashing is when it has a lot of page faults.
Yeah, when we have excessive page faults, lots of page faults. What's wrong with that?
Make the system slower.
It makes the system very slow. Most of the time it's just swapping pages. But what's so slow about swapping pages? Why is swapping a page is a slow operation? Any idea why? Any idea why swapping pages is bad, is slow?
because pages are in part right, so you need to move them part right.
Because the page swapping or page fault will require reading and writing from the hard disk or to the hard disk. And the hard disk is a very slow device compared to main memory. That's why thrashing is really bad. Why is it bad? Because slow. Why is it slow? Because we have to use the hard disk. Now back to your question. What are the steps when we have a page fault? The memory manager calls a page fault handler. What does the page fault handler do? Can you tell me? Can you tell me? Page fault handler. What are the steps that the page fault handler do? Any idea? Guys, listen to the answer. Yeah? Hold on, I can't hear you. Talk. Camus, please. It checks first if there is a free page frame in memory, so we just bring the page and put it in it. That's the first step it does. Do we have a free space in memory? We call it page frame, allocated to this process, that we can just go and bring the page and put it in it. Now, let's say the answer is no. What else does it do? What's the next step? Does a page fault handler do? Any idea? Come on, hands up. Yeah? The page fault handler, what does it do? It's gonna bring the missing page, the requested page. But first check, do we have space to bring it into? And if there is, just go and bring it, read it from the hard disk and put it in main memory. But if there isn't, the next step is it says, checks, all right, there's no space, so there's 3 or 4 pages occupying all the space. I have to pick one of those pages and take it out. So the next thing, it has to decide which of the pages in main memory needs to be brought out. And after it decides which page it will take out, what's the next step? It needs to decide first, right? First, do we have space? If there is, just bring the page in. If there isn't, well then we have to look at the pages that are already occupying those spaces and pick one of them. And we say, you need to go out. Now what's the next step? Does it take it and write it out to the hard disk? It has to do one other thing, because now it needs to write it to the hard disk and read from the hard disk the requested page. So there are 2 operations we need to do with the hard disk. One is writing to the hard disk, and one is reading from the hard disk. The hard disk is very slow, so we try to skip one of the steps if we can. So maybe we shouldn't write this page out to the hard disk because there is a copy of it on the hard disk. Why do we bother writing it if it's exactly the same copy? So that's why it checks the next thing first. Has this page been changed since the last time we brought it? So we know. Stop talking, please. So next time, every time we bring a page up from memory, now we have exactly the same page, the same copy. So if we have to write it down, there's no need to write it. It's exactly the same copy. But sometimes while the page is in memory and the program is executing that page, sometimes it changes the content of the page. So if the page has been changed, then it's different to the one in memory. We have to on the hard disk, and we have to write it back. If it's exactly the same copy, there's no need to write it back. So the memory manager, anytime it modifies a page in memory, it goes to the table and say, yeah, this page has been modified. So that's what the page fault handler does next. First it checks, is this page, has it been modified, or is it exactly the same copy as it is on the hard disk? If it is modified, then it has to write it to the hard disk. There's no way of skipping that. But if it's not modified, that means it's exactly the same copy. There's no need to write it, and we skip that part. And then we go to the next and last step, and that's go and read the requested page from hard disk and put it in main memory. Anybody can re-list those steps for me in a logical order and the right order? Anybody want to try it? The page, we need a page and it's not in memory. So on the hard disk, we call this a page fault. So the memory manager calls the page fault handler, and the page fault handler comes in and does those steps. What are the steps? It knows it has to bring that page from the hard disk to main memory. But what steps does it follow? I've just said them. Anybody care to repeat them? Hands up. Okay, make sure you know those steps. Another question. If the policy is we take out the least frequently used page, the page that has been used very little in the last second or two. Some pages have been called 10 times, some pages are never called again. Once they went the first time in memory, then we never really called them or referenced them again. How does the memory manager know how frequent, how many times a page was referenced in the last second or two?
Check the bytes. Which one was the last one, on byte.
So it checks a field, a frequency field in the table. There's a field that keeps the frequency, and which one is the most or least recently used. So it's the same field. So it's just one byte. It looks at ones and zeros in the byte, and every time a page is requested or referenced, the memory manager going to turn the left bit to 1 if it's 0. If it's 1, it leaves it at 1 for that page. And then every now and again, for all the pages, it does a shift to this field for all the pages. So if a page is not requested, the left bit will be 0. If we shift it, then we have 2 left 0 bits. If it's shifted again and not you called or referenced, then there'll be lots of zeros on the left. The one that's called so many times, it will have lots of 1s. So the one that has higher number of 1s, then is the one that's more frequently used. We talked about this last lecture. All right, today we start a new topic. First, I put in practice questions for you on Moodle. You can ignore them if you like. You don't have to read them, but I recommend that you read them and you try and answer them on your own. You don't have to submit them. You don't have to send them to me. There's no mark for doing them, but it's good for you to do. And maybe next week or the following week, I'll put in the right solutions for them. So check out your solutions with the correct expected solutions. All the solutions are from the notes or from the internet. You can search it, Google the solution if you don't know. It will be studying for you. It will cover the introduction part that we had to operating system, and it will cover memory management. So do go through them. I recommend that you should go through them. In the meantime, I'll be placing a tutorial this week. So keep your eye on Moodle. Have a look at Moodle every day, once a day at least. And once I put in a tutorial, you have 1 week to do it. In fact, you have 4 days, but I give you 3 extra days. So almost you have a week. But officially you only have 4 days. But even if you submit it in 5 days, it's okay. In 6 days, there'll be no penalties. If you don't submit it in 1 week, it's finished. You don't have to submit it. It will not be accepted. So make sure you submit a tutorial. But those practices, questions I gave, you don't have to submit them. They're just for you to study. Any questions so far? Okay, today we start looking at another topic. The processor manager. So today we start looking and talking about the processor manager. And the processor manager is that manager or part of the operating system that gives the best use, try to provide the most efficient use of the processor, which is the CPU. And usually the CPU is the most complex part maybe of the entire computer and possibly the most expensive part as well. So utilizing it the best possible way is a great objective if it can be achieved. So we look at job scheduling or processes scheduling, and we look at the insides of the processor manager, which has maybe at least 2 schedulers. So the processor manager, mainly it schedules the CPU between the different processes. It tells each process, but doesn't have to tell it, but it actually allocates the CPU to each process or each job in the system as the processes are running. The advantages and disadvantages of process scheduling algorithms that are preemptive versus those that are non-preemptive. So we'll look at what's meant by preemptive systems and non-preemptive systems. The goals of process scheduling policies. We look at different scheduling policies and we see the difference between them and their goals. And we look at a number of scheduling algorithms and we see advantages and disadvantages of each one of those. Right, so go back again. We know what a program is, or what a job is, and what a process is. So a program is a unit of work that has been submitted by users for an operating system. A program is not active yet. A program is a list of instructions written in a file, stored on a disk that's inactive. We call that a program. So any file that has a list of instructions, we can call it a program. But once it's submitted, can you please stop talking, you? Next time I'll ask you to leave if you keep on talking. Or come and sit here beside me. Shukriya. Right, a process or a task, sometimes it's referred to, it's an active entity, an active program. So a program is inactive, this one is active, it's been allocated memory, it might be allocated CPU, it will do some work, and some of its instructions will be executed. a single instance of an execution program, they call it. Maybe this is right. A processor is the CPU itself, is the one that will execute the instructions. It performs calculations and executes instructions of programs. In a single user system, the processor is busy only while it's running one job. But most of the time, this processor is really doing nothing, because it runs it so fast. It runs through million instructions in 1 second, and then you need to do some printing or reading something off a keyboard, and it might take 5 seconds or 10 seconds to read something from a keyboard, or that much time to print a couple of sheets of paper on a printer. So those 5 or 10 seconds, the CPU is doing nothing if there was only one program. So it's a waste of time, and therefore multi-programming environment is used a lot. Almost all computers today, they are multi-programming environment. They will run more than one program, a number of programs. So in multi-programming environment, a processor is one processor, but it must be allocated to each job or each process in a fair and efficient manner. Sometimes fairness is not always good. Sometimes, if you're fair, then the system becomes inefficient. But we try to make it as fair as possible and as efficient as possible. And most of the times when it comes to business, efficiency is more important than fairness. Anyway, in this system, it requires a scheduling policy to decide which program, which process should now get the CPU. So there are a number of different scheduling policies that we will look at. There are also something called interrupts is used a lot in operating systems. An interrupt is if there's something, if you need something or something goes wrong, an interrupt is issued. All operating systems almost use this technique. Like if, for example, if you want a printer, you can ask an operating system, is the printer ready? Can I use the printer? Can I use the printer? And the operating system say no. And then you ask again, and the system will tell you no. Maybe for 2 or 3 seconds or a minute, until one of your questions, then it'll say yes, the printer is free, there you are. But what's wrong with that? That's like you're doing nothing. It's like waiting at traffic light and the engine of the car is running, waiting for the red light, for the green light to switch on. And for each time thereabout you think they're going to switch on, you rev the engine, you're going to drive, and you're only going nowhere. You're waiting in the same location, but you are wasting energy, you're wasting petrol. So saying, if you're asking the operating system, I need the CPU, is the CPU free? And the operating system say no. And then, is the printer free? No. Or I need that file, is it available? No. Is it available? No. Each time you ask the question, is this available? You're actually using the CPU. CPU goes out and runs those 10 instructions to see if the CPU is available or not. So you're actually using the CPU. Just like when you stop in a traffic light, you're not driving anywhere in a car, but the engine is running, you're burning fuel, even though you're going nowhere. So that's not a good technique. So all operating systems, they say, they follow this system. They say anytime you ask for something, if it's available, it will be given to you. You only ask once. If it's not available, you'll be knocked asleep, and they'll leave a timer or an interrupt, and they say whenever that thing is available, we'll wake you up. So you're only allowed to ask once. So it's so efficient, so you'll never use the CPU again, asking for the same thing. Sometimes you have to ask 1,000,000 times. But every time you ask, you use the CPU. That's not an efficient way of running business. So all operating systems, they say ask once. If it's available, you get it on the spot. And if it's not available, you will be put to sleep until that thing becomes available. This is almost all operating systems use this technique. And the interrupts allow that. So interrupt is a hardware signal that suspends the execution of a program. It's like you go to sleep, it's you're suspended. And activates the execution of an interrupt. As well, there's an interrupt starts working, either like a timer, or it puts a signal request with the operating system. Whenever that thing happens, give us a call, give us an indication, or give us a wake-up call. So that's really what an interrupt is. You can ask for interrupt, you can ask to be put to sleep and be awakened in 3 seconds if you like, or be awakened when something is available, when another program runs or something like that. Then there's something called context switching. A context switch is saving a job's processing information. So if a process is running, is executing, and then it needs input. So we have to take this process out until the input becomes available, and then we need to bring it back in. But while it's out, the CPU, we give it another process, starts running. And things change inside the CPU. And another process comes in and runs. So this, the first process we took out, we stopped, for example, at line number 200. Now we brought in another process, started running, and ran to line 2000. So when we bring that process back, the CPU thinks, hey, am I at line 2000? No, we got process first that we stopped it earlier, stopped at line 200. So we need to take a note of this piece of information. So when we bring it back, we put it up, we put this information in the CPU again. Remember, the CPU has CPU pieces of memory. They're called registers. They hold information that's only useful and needed by the CPU. So if a process, you've reached line 200 and you took it out, save this number, because later on when you bring it back, you go to the register where it says line number and put that number 200. So the CPU starts executing exactly at the same line where it stopped the last time. It's like maybe again in the hospital, patients that come in and maybe they need to do 3 operations, one after the other, to each patient. So you do the first part of the operation, maybe the first part cleaning up or something, then say take them out. And then later on is brought back. And we should know what that patient had earlier on. Now we do the next part. So the point is that in operating system, we need to keep the information in the process that was using, that is now, right now, using the CPU. If we stop it and we take it out, we need to save all the information. There's some pieces of information that are required. One of them is what line number have we stopped at? And if we were reading, if this process was reading from a file, which record is it reading right now from that file? So, for example, it read up to record number 16. So when we bring it back and say read from that file, we know we go to record 17. We don't start from the beginning. The same as, so basically we should put the environment inside the CPU. The environment where that process has stopped, we should copy it and save it for this with this process. And if we bring another process, we take the saved environment and put it in the CPU. So that process thinks, okay, things didn't change since the last time it ran. Remember, most processes are asleep, they're doing nothing. Only when they are being executed by the CPU. So it's like you go to one place, one location, one building, at, for example, 9 o'clock at night, so it's night, so they have the lights on, everything, and it's nice and clean and tidy. And then you leave and come back, say, a week later, exactly at the same time, even though that building has been used so many times, been dirtied and been, you know, maybe things broke up. But if they can fix everything, put it back the way it was, and put the same lights on, you come in, you say, oh, the room is exactly the same. That's exactly what each process comes into the CPU, run for a while, has a couple of files open, has reached certain line of coding, and then we take it out. And the CPU is so busy doing so many other things for that process, but when we bring this back in, we should put everything back the way it was when we took it out. How do we know what the information is? We save it. Before we take the process out, we write everything. What time did it leave? What time did it use? All these pieces, maybe if it was for us, for people, you say, okay, what's this lightness outside? Was it bright or dark? We take the exact moment of time and maybe which lights were on, which windows were open. So when we bring you back in there, we do exactly, we leave everything the way it was. So even, for example, if somebody goes to sleep, if you go to sleep in this place, right, and windows are closed or whatever, one of the windows is open, one of the lights is on, and then we take you out, you sleep, we bring you back another time, we put you here, we put everything back the way it was, you'd wake up, you'd think, you never left the place when you probably left it. That's what happens really to programs. They leave, they're asleep where they left, they could go for a second or a minute, which to us is like a day or a year, and then we bring them back. But we put everything back the way it was. So that's called context switching. Context switching is every time the CPU stops working on a process and that process needs to go out, we save the environment. We save all the information belonging to at the CPU that belongs to that process. We put it with it, like in a label, like in a file, like a patient in a hospital. The patient is asleep, he doesn't know nothing. But they take the file, they sign everything, they put all the information, we did this, and this is what the medicine should be taken, and they put it in a file or a folder on the bed or a trolley. It goes with the patient. Bring in the next patient, they'll open the file and say, oh, this patient was here last month, and we did this and we did that. Okay, switch this, switch the oxygen on. No, this guy doesn't take oxygen, So they set the environment for the patient since the last time, based on the information that was saved the last time that patient was there. Okay, same with programming. Every program or every process, when it leaves the CPU, we save the information that belongs to that process in a label that goes with the process. It's called process control block, PCB. And we write all the information and it goes. And when we bring the same process again, we open that PCB. Instead of patients in a hospital, they call it file, but here we call it process control block. We open it and we say, okay, this process, this is where last time it was here, we switch everything, say run. And then it wakes up. And the process never notices any difference, because everything is back the way it was, and runs for a few more seconds with the CPU, then stops. Save everything again on its PCB and send it out. Bring the next process. So this happens all the time. So this is called the PCB, where the information is kept for a process. It's called the PCB, the process control block. All right, so the memory manager has a processor manager. One of the managers that work for it is called the processor manager. It's like the prime minister in the government. He has a health minister who looks after health and whatever, sports minister. Here in the operating system, we have the operating systems like the prime minister, and it has many managers. We looked at the memory manager. It's the guy who looks after memory. Now we're looking at the processor manager. And the processor manager, its main job is to schedule processes. Schedule, I mean, okay, you're next, you're next, you're next. That's scheduling. Everybody knows when it's their time to go and start the work on the processor. The processor is allocated to them. That's scheduling. But it has actually two schedulers. And in some systems they have even three schedulers, because there's a lot of work for a scheduler. But let's look at the systems that have two schedulers, and you get the overall idea. So first, they have what they call the high-level scheduler and the low-level scheduler. The high-level scheduler is also known as a job scheduler. So it's the one that schedules jobs, and another one that schedules processes. What's the difference between a job and a process? Any idea? What's the difference between a job and a process, or a program and a process? Yeah, and the job or the program?
Set of instructions that are stored.
Okay, a program is just before it's submitted. When it's on the hard disk, a program, it's like a process. It has instructions, but it's doing nothing. It's idle. It's not gone into the process of execution yet. So when you submit a job first, it's still not running. It still has no memory. But once it comes into the system, then we start dealing with it. It's still a job, but we'll turn it into what we call a process. That means it's like a person out in the street, they want to become a student. They're not a student yet. They come in through the initial part. This may be here in college we call it registration. You start registration, they ask what's your name, what's your qualification and all that. And we give you space, we give you a key for this is the gym, this is the restaurant, and here now you become a process, right? But that's still not a process yet. At that stage, it's just a job. And then it becomes this process, and it comes under the responsibility of the process manager. This is like in a university, they have a registration office that deals with people outside college. Once they register, they become students, then they become under maybe the faculty kind of students in some faculty, and they'll be treated so. So also, the processor manager has at least those two schedulers, or two subsections, or sub-managers. One is called the job scheduler. So basically, the job scheduler looks after new processes being submitted, or new programs that are submitted for execution. Exactly like the registration office in a university. It deals with newcomers. And what happens here, we'll see what it does, try to improve. Obviously, everything is for the improvement of the efficiency of the system. And we'll see what the job scheduler do and what the processor scheduler do. In fact, the process scheduler is the one that really looks after the CPU. That's the one that does the main job. It's low level, it deals with bits and pieces. And it's, hey, you take the CPU now, you go there, I'm moving you to the other queue, and then the CPU, so the one that gives the CPU is this part. This part here doesn't really deal with the CPU, it just deals with the new counters, the new programs submitted. But it does a good job of them. What does it do? And here's what the job scheduler do. It initiates a job based on certain criteria. So it starts a job that becomes a process, but upon some criteria. And the criteria are, for example, the size of the process. It might say, sorry, we can't take you, you're too big, we don't even have memory for you. You're bigger than the memory we have. Or and there are other criteria. Are you a CPU bound or an IO bound process? Whoa. Do you know what the CPU bound process is?
It's a program. It's a process that requires a lot of CPU, but there's
A little IO.
yeah.
And you know what an IO bound process is? Go on. You do? You know it? Okay. Right. What's an IO bound process? It's a process or a program that needs a lot of input and output. It deals with IO devices and very little CPU. The CPU bound is the one that needs a lot of CPU and very little input or output. Right. So there are a number of criteria that this guy checks out. And also, it strives or puts jobs in a sequence that use all the system resources. We've already talked about that before. how do you make all the resources usable and are in use? Like you have the CPU and you have I/O devices. So don't just send I/O devices only, I/O bound devices. That means the printers will be busy and the CPU, nobody's using it. So it's better to send I/O and CPU bound processes at the same time together. So it kind of holds the programs, the job scheduler, it holds them as a group and then start picking them up. Oh, you too, you better go now. And they start moving. So it picks an I/O bound and a CPU bound. Why? Because if you have a group that wants the CPU, they'll be using the CPU, and the other one are not waiting behind them, they're actually using the I/O. So first, all the processes are busy most of the time, and our resources are being used all the time. It's better than having all the programs that are there, they only want CPU, they don't want I/O, very little I/O. So all the I/O devices will be idle, nobody's using them, and there'll be a long line on the CPU. Everybody waiting on the CPU. That's not really the best system. The best system when everybody is happily working, doing what they need, and our resources are also busy. So strives to balance a mix of jobs with large I/O interaction and lots of computation. So that's try to mix the jobs that are going into the system to be a mixture of I/O bound and CPU bound. Also tries to keep most of the system components busy. So by sending a balanced kind of mixed groups, then everybody will be happy using them. It's again the same as if you're going for a game place where you want to have fun, one of some of those places where you might have snooker table or pool table, and you have what's another game they have, maybe darts or table tennis, ping pong. So you have those two tables. If everybody wants to play ping pong, then nobody will be playing pool. If everybody is playing pool, then they'll be sitting waiting on the two who are playing, and yes, the ping pong table is not used. So you need to have all the resources used as much as possible. That's called utilization. And you also don't want everybody queuing for the same thing. And when hopefully if we had different people or different users, they'd be happy to be using the other table at the same time. So that's really what we're trying to do. Try to keep everything in the system, all the resources busy, and also all the processes happy instead of waiting. The low-level scheduler, the other one, this is the process scheduler. It determines which jobs will get the CPU. So it's the process scheduler, the one that will be getting, or low-level, the one that looks after actually scheduling the CPU. It decides when a process should be interrupted as well. So sometimes, guys, you give the CPU to a process, and you have a line of processes waiting for the CPU. When you give the CPU to a process, you know this CPU is going to stop. Sooner or later, it's going to stop by itself. You know why? Why does a process that has the CPU running and decides to stop by itself? Any reason? Any reason? What's your name? Say it again. Naheem. Okay. Tell me, Naheem, why do you think a process has the CPU and is executing and it's like, okay, I don't want the CPU no more? Why would the process do that? Any idea?
Maybe it needs something
Such as?
another function to run.
Maybe it needs I/O. There's nothing else except I/O. You either need an I/O or CPU. Every program will take the CPU, run it, or we know for certain it will have to stop. But remember I told you many weeks ago, if a process does not need input or output, it's a waste of a process. Every process must use some input, must read a file or a keyboard or get information from a communication line or something, or else it's a wasting process. And also, every process, if it runs, it must stop and print something or generate something and send it through a communication line. Otherwise, if it produces nothing, it's a waste of a process again. So we know every process, we give it the CPU, it's run after a short while, you say, okay, stop, I need input or output. And that's what we are banking on. And that's what the scheduler here does. Give you the CPU, and when you stop and you say, I don't need it no more, I need something else, say, okay, go and wait for that, and give the CPU to the next process, and next process. That's what that scheduler does. But sometimes a process doesn't stop, maybe for a very, very, very long time, and delays everybody behind it. It delays all the other processes. Like a process, yeah, maybe it will need I/O, but later on, after 2 minutes like 2 years in our time at the CPU. So you have the CPU running, it's like you say to the guys, okay, I'm gonna borrow the car, and they say, yeah, take it, we'll use it when we come back, and you go for 2 years, not 10 minutes or half an hour or an hour or 2 hours in our time, but 2 years, that's way too long, that's not good. So something can happen also in processes in a system. So in that case, what happens, the memory manager, or sorry, the CPU manager, the processor manager, will interrupt that process, say, hey, that's too long, stop. And it can actually stop a program while it's executing, if it goes beyond a certain time. And that certain time is known as a quantum. We'll look at it later, but remember, a quantum is the maximum time a process is allowed to use the CPU, once it has the CPU. Okay, of course, we expect you to finish before then, but if you don't stop voluntarily, if a process does not stop by itself and say, okay, I need input, I don't need the CPU anymore, well then, most systems, they have a setup of time, and it's known as a quantum. It's, again, the administrator will set that time. It could be 100 millionth of a second, or maybe 250 millionth of a second, like a quarter of a second, or something like that, or 10% of a second. So if that process keeps the CPU for that long length of time, we will interrupt it. So this guy here decides when a process should be interrupted and determines which queue the job goes in. Because when the CPU, when a process is using the CPU and then it needs something, it might need to print something, or it might need to read something from a hard disk, or read something from a keyboard. And every one of those devices, input-output devices, they have a queue. There may be 5 processes waiting for the hard disk, and maybe 7 processes waiting for a printer. So we move that process and we put it into another queue for those who are waiting for that. It's like you go to a hospital, you go into the operation room, and they say, no, see, we need you to go now to have an X-ray. So you're taken out in a trolley. There may be blood analysis in this place. No, you're going for the other queue, the queue that's for the X-ray. And you put there at the X-ray, you do nothing. You're just asleep in a trolley, same as every other process that it says I need input or output. The process itself is asleep. We just bring it to that location and stands in a queue. Maybe many other processes waiting for that, for those jobs, for the service at this point. And then once the job is done, it's read, we bring it back into another queue, waiting for the CPU again. So this guy is the one that decides, okay, if I take you from this CPU, you're going to go to one of the I/O queues. I decide which one, and it gets it puts it into that queue. And it recognizes when the job has concluded. Like you say, okay, go and print something. So we put it in the queue beside the printer. And that process is asleep. But we know when it finishes, because you put that request like an interrupt with the operating system, and when that printing is done, the device manager, there's another manager, to say, oh, who is waiting on this job? Oh, it's that one. Okay, give them an alarm or something like that. They give them an interrupt. They, guys, your job is done. So the memory manager comes in and says, oh, this process that's asleep, I was waiting for that printing. The printing is done now. All right, I'll take it now and move it somewhere else. So interrupts are used a lot to signal kind of starting operations or requests for some function, or that function is done by the server, whoever is doing that job. So this just says there are jobs that are known as IO-bound jobs, and they have many small CPU cycles, but big or long IO cycles. That means they need the CPU for a little time and IO for very fast. But remember, it goes in cycles all the time. This is what happens. You get the CPU, you're given the CPU, use it for a short time, and then you move to IO. Then use that IO, and then come back, brought into the CPU again. Use the CPU again. So, like a process might go into the system, it might use the CPU 220 times, maybe. That's okay. So fast, it keeps it moving. But they are brief. If it's CPU bound, then it will need a lot of CPU time. And if it's IO bound, it will need less CPU time and more IO bound. And the total effect of all CPU cycles from both IO bound and CPU bound jobs approximate to a certain Poisson distribution. It doesn't really. But this is really what the length of time, approximate length of time that it takes for a job to go through CPU and IO. So normally, if this is CPU bound, it will hold the CPU for a long time. It will use CPU and only needs short IO bound. And then more CPU. So these are the CPU bound processes, the programs that need a lot of CPU. And then we have the IO bound. They only need the CPU for a short time and then a very long time of input or output, and then another piece of CPU, and then another long time of IO bound. Some schedulers have a third, some systems have a third scheduler, removes active jobs from memory, allows jobs to be completed faster. Okay, don't worry about it. Now, when any process goes into execution, it passes through those stages. Just maybe like a student going into a college, they might, like an applicant, maybe under processing, and then ready, that's somebody who's studying, they might go on the break during the summertime, and then come back again, and I keep on, once a new student, then ready to start studying, and then you could be waiting for your lectures or your semester, then you do the semester, go back, wait again for a summer holiday, come back and finish again, and you might have to go through this cycle a number of times, and then you finish and you graduate. So that's the steps or stages or states that maybe a student goes through, but also a process going into a system. So every time you run a program, you double click on some icon to execute a program, it goes through those steps. A holding state, that's the high-level scheduler that starts taking information about the program and allocated certain things like priorities and names and ID, just you're given, like yourself, given a student number and things like that, and any other requirements. And then it's ready to start running. And if it runs, then if you're using the CPU, if it needs an IO, it goes into a waiting state and keeps cycling through those until it finishes. So this is the actual diagram, the state diagram for a process execution. So every process because now from now on at this stage, it's a process. It comes in as a new whole. So some books or some textbooks, they call it the new process, or some they call it the holding state. So the process, like you a new student, you're just doing your application. You haven't become real student yet, a new person to come into the system. So any process that comes in first, from the moment you double click on that icon, it becomes a new process. Or in a state called new, or in a state called holding state. And this is handled by the high-level scheduler. This is the one that looks at these. See, in most systems, those two the states, the new and holding state, and the ending or terminating state, they're handled by the high-level scheduler. The lower-level scheduler looks after those three states down here in the middle. So this is what happens to a new process comes in. A new process arrives to a system, is received by the high-level scheduler. So you can call them high and low, or the other two names that we use, job and processor schedulers. So the high-level scheduler will look after the job, will take it, identify it, and give it an ID while it's processing in this memory system, in this processing system. It will be given an ID. So this process is known by that number or identifier, and it's checked for other things. It is given a priority, how important is that process is. Like sometimes in some scheduling, who gets the CPU? Sometimes it's the more important job gets it. So you get a priority at that stage, and so on. So, and when a process is finished, ready, the system identifies it, it creates, it's like when you go into a hospital or a college first, they open a new file for you, and they start putting your information in that file. Here they also create something called the process control block. So the process control block is created as soon as the process is submitted into the system, right? That's the new state, or at the holding state. And it's created by which scheduler? Which scheduler do you think creates the PCB? The process scheduler or the job scheduler, or the high-level scheduler or the low-level scheduler? You think it's the high, yeah. So it's at this point, the high-level scheduler identifies the process, gives it a new ID, and creates the PCB for it, which is a PCB is, and somebody asks you, what's a PCB? It's not a file, it's a data structure. I don't know if you started programming. A data structure is something in memory. Let's identify, you can link them together to make a list or put them in a queue. But a data structure is not a variable, it's not a file, it's like a variable, but it's a kind of biggish variable. So it's like a record. You write the ID, the priority of this process, what time it came in at, all this information. And in fact, it's that PCB is the one that we say, okay, the process moved in a queue, waiting on a printer. The process, the code never moves. The code is put in memory. Remember, wherever it is in page 15 or page 250, that code never changed from that location. We don't move it. When we say put the process waiting in the queue, it doesn't mean, hey, let's take the code and put it in the queue. No, you only take that label, that PCB. So it's like in a patient, for example, if we get to a stage where we don't move the patient, we just send its folder, the file that belongs to that patient. We know, or your record somewhere here. They say, oh, we know this guy is in second year. They didn't move you, you're already in second year, but they move your folder, they put it in a drawer that says second year students, we move it there. Or when you finish and graduate, they might take all the folders and say, well, you're going to graduate, and put them into another small press or drawer called graduation students. So they keep moving your record. Same here with a program. When a program goes into a page or somewhere in memory, it stays in that place. We never really move that code as such. Whenever we say, oh, the process is moved, we mean the PCB is moved, right? But that's what we refer to. Okay, so that's just few things are beginning to come up. I want you to get the right idea to know exactly what's happening. All right, so the process, once a new process comes in, it's given an ID, we create a PCP, and we give it a priority, and then we decide, okay, try also to identify, is this process a CPU bound or an IO bound? And then the new, the high-level scheduler will say, maybe take two. IO bound, CPU bound, and say, I'm sending you now. You're on a different, you've finished the registration. You've finished the initial work that needs to be done with you, you go and run. But you can't send it to the CPU. That's where the CPU is. You have to go, you go in a queue waiting for the CPU. But everybody in this queue, they're ready to run. Ready. They call it the ready queue. That means they're not waiting on nothing. They're not waiting on input or output or anything. They're only waiting on the CPU. If the CPU is busy, it's free, and if it's their turn, obviously there'd be a queue here, and the CPU, only one process is there. Only one process can run in the CPU, is in this state. And once the CPU says, okay, this says I don't need the CPU, it's taken out, and one of these processes is sent in. Okay, so the ready state is the state where every process is ready to run in the CPU. And remember, a process, so it starts at the new state, it's initialized, a few bits and pieces are done, including creating the process control block, and it's moved to the ready queue or the ready state. In the ready state, that process is ready to use the CPU if the CPU becomes available, and if it's in the right queue. So that's a queue. Sometimes it's just called the ready queue. Inside there is a queue. You go in and join the queue. Of course, if you have high priority, you might be put to the front of the queue. Or there might be two queues in there. We'll see later on. There might be 2 or 3 queues. High priority queue, low priority queue. So you join whichever queue based on your priority. And then when this is free, the CPU, one process is moved in. So it runs in the CPU. And if it doesn't stop, if it doesn't give up the CPU by itself, sooner or later it'll be interrupted and taken back and put back at the end of the queue. And that's called, that's when that, if it exceeds something called the quantum. So if you have a process that's running on the CPU, every time the process starts running, we put a process in the CPU, the memory manager, the scheduler, the low-level scheduler will start a timer for it. And it expects it to leave the CPU by itself. But if the time reaches a certain point, what's that point called again? What's the maximum time a process is allowed to stay at the CPU? Quantum. That quantum. So if a process exceeds the quantum at the CPU, the low-level scheduler will interrupt it and put it back in the ready queue. Say, okay, you used it too long. Come back here and put it at the end of the queue. Give the others a chance to use the CPU. And if the others finish CPU, quickly to get the CPU again. Okay, but most of the processes, they will not exceed the quantum. They will say, hey, I need some input or output. We say, okay, we'll move you down to the blocked state. Or sometimes they call it the waiting state. There are 2 names for it. That means, what's the blocked state? That means you're blocked. You can't use the CPU because you need something else, an input or an output. Maybe you want to read something from a hard disk, or maybe you're waiting for a picture from a camera, or a scanner, or a keyboard, or some input or output devices. So blocked or waiting, they are blocked because of an I/O device, or waiting for an I/O device to finish. We put you in the right queue. Of course, the process, once it leaves here, it's not running anymore, it's asleep. So it's just put in the right queue. And remember, we don't put the process itself, we only put the PCB of the process. We move the PCB. So it sits here waiting for that until that's done for the process, and then we move it back to the ready queue, joins the ready queue, and it gets to run it, the CPU again, blocked again, goes back to the ready queue, and keeps cycling through this. This cycle is handled by the low-level scheduler, or the process scheduler. Until at some stage, it says, okay, I'm finished. I've executed my last instruction, or it does something wrong. Like if this process is running and say, okay, put this value in my memory, in memory location 17,000. And the memory manager will say, hey, 17,000 is not your memory, someone else's memory. That's an error. That's an unforgivable error. You're finished, out. So a process at this point of running can finish normally, absolutely good. And if it finishes, it's moved to the ending state, or to terminated state, or finished state. So they have the same name for it in different books. And sometimes it doesn't finish normally, but it finishes because it committed an error, and therefore it was terminated, not finished normally. So a process can either finish normally or finish abnormally. How does it finish abnormally? If it commits an error, the operating system will terminate it, and the scheduler will move it to the terminating state. So the terminating state is like the graduation state. Hopefully you all will go through at some stage. That's when you finish, you pass all your exams, your subjects, you're still a student, but you're not really a student. You're graduating. You're waiting for yours just to get your degree, and that's it. So same here. When programs finish running, they don't just disappear, all done. So we can take them, usually in most systems, in most operating systems, they'll be taking the time. So every time you go into the ready state, the time is noticed, written in your PCB. And then every time you get the CPU, it's written what time you got into the CPU. You got interrupted or out, you leave, we write the time. So we always know how much time you spent at the CPU, how much time you spent waiting, how much time you spent in the ready queue waiting on the CPU. And then all these times are taken and kept in a log. A lot of the times this information is important for later on, for maybe improvement of the system, or the detection, or investigation. Sometimes your file is missing. So who terminated it? You might have to go through those and see which file was running, when you came in. If every time you open a file, it's written again in your PCB. You've opened this file at this time, you closed it this time, you added a record to this file, you deleted the record this time. So all this information is written in your PCB while you are executing. But when you get to this point and you finish, we take that information and write it down in a log. They call it the log. This is just information about normal execution of everyday execution, every process, what time it came in, what time it terminated, what time, how long did it spend in the ready queue, how long did it spend in the CPU, how long did it spend in waiting for I/O, blocked, that is. See, remember, that one is ready, that's blocked. Ready because CPU is not available. Blocking is for I/O, but work is being done on your behalf. Like maybe you're waiting for a print, while the printer is printing, you're just asleep for that length of time, and then you go back. So all this information is written out in a log file. In every IT department, every computer center has a log. You can look at it later on. Probably nobody looks at it most of the time, but you can look at it, and you might get information out of it. What's the average turnaround time in today? How many processes did we run? What's the turnaround time? Anybody remembers what the turnaround time is? Okay? You remember, right? Yeah? Yeah.
The time it takes for process, like from the beginning to the end of it.
Exactly. So turnaround time is from the time you send the process there at the start until includes everything until the time it finishes. So it includes CPU time, which is only the time you choose the CPU. It includes all the waiting time for IOs and waiting for CPU and so on. So this is really what happens in a system there. And finally, before you're released, before the process is terminated, we delete the PCB for that process. So the PCB is a data structure, probably that can be put in a list. So it's handy enough to put them in a queue here, so there'll be few PCBs and few processes. And then, remember, if we need to bring a process here and start running, we're going to put the CPU suitable for this process. Then the information is in the PCB. We put them out in the CPU registers. Remember the context switching we were talking about? So if a process is running here and is doing few things, and then says, okay, I need I/O, say, hold on, before we take you out, we take all the information. What file have you opened? What record have you been reading? The last record you read? Which last line of code you've done? How much time you spent at the CPU? All these times are kept in its PCB. We read it from the registers, but copy it onto the PCB. Take it out and bring the next process. The next process has its own PCB, has the information of the last time it was in the CPU. We take that information and put it here, and then start running. It's like you go to a restaurant, there's this table or this, only a restaurant only to serve one person or one family. And last time you were there, they know, oh, you like Indian food, you like, whatever it is, you like this drink, so they put everything saying you don't like strong lights, they dim it, and then you finish, you go. They write how much you ate and all that. Another family comes in, they take their records, say, oh, they like bright lights. So that's what I mean here by setting the environment. The one that's going, you save all the information. How much did they do? What did they read? All that information, send it out. The next one comes in, start taking information from them and put it in the CPU. So the environment will be ready, correct for the next job. This is called context switching. So context switching, it means the process that has the CPU, when it's leaving the CPU, we save the information, the execution information from the CPU onto its PCB, and it goes, and then the next process comes in, we read the information from its PCB and put it in the CPU so it can run, continue running with whatever it was doing before. The only thing, guys, this context switching takes a bit of time. And if you have a lot of context switching, and it's a wasted time, nobody can run. The CPU has to wait until the place is prepared for the next patient, kind of thing. Like if you do this in a hospital, and this is the operating room, every time you take a patient, prepare the room for the next patient, maybe there's cleaning, there's produced blood, this new patient needs more blood or different type of blood or different type of machines, bring all these machines, set them up. Might take half an hour to set it up. That's a waste of time. You should be operating. So we try and reduce this context switching. Remember, if a process spends here more time up to the quantum and we only take it out, that means we are doing less context switching. It's good in one way to allow a process to keep the CPU for a long time. That means we didn't do any context switching. CPU was utilized more. But that may not be fair on other processes waiting. Like if you have really short processes and one of them is long that comes ahead of you, it's going to delay everybody. Like going to a supermarket and you just buy a packet of cigarettes or a piece of chocolate, one drink, and you're all in one line, 10 of you, one item each. but in front of you there's this big trolley, and the cashier is there. So everybody gets delayed because of that long one. But from CPU perspective, it's better because it's less context switching. Why? Because context switching is a wasted time. The more context switches you have, the worse for the performance of the system. But if somebody keeps the CPU for a long time, it's bad for the overall average turnaround time. So we have to operate, with a bit of leeway, or you have to worry about a few things. So this slide just tells you what I've been saying, a bit less than what I was saying. This is a bit more kind of image that describes it. There's at the new state, when a process comes in, it joins at the new state, joins, and after it's created, and we'll create a PCB for it, we put it in memory, it's located in memory, but we create a PCB and we give it priority, and you need to remember some of the things that happen at each state. Right, just some of the things that happen at that state, the new state. Anybody remembers what happens to a process at the new state? Give me one thing. What happens to a process when it first comes into the system at the new state? Yeah. Pardon? We give it a PCB. We create a PCB is created for that process. That's a process control block. Anybody knows what a PCB is? You know what a PCB is? What's a PCB? Process control block. What is it? What does it do? Is it something that runs? Is it something? What's a PCB?
It's a data structure.
Pardon? It's a data structure. And what does it contain?
Information
about the system?
Information of jobs processing.
Information about one process. Just like your file of a student when they first arrive to a college or register, they create this file for you. And it contains all information about you. Your performance, your exams, your sickness, your attendance, everything goes into that file. So saying PCB is created anew when a process comes in. When is the PCB destroyed? When do we delete the PCB? Any idea? The PCB is created when a process comes in at the new state. And then we delete it eventually. When is it deleted or where? It's deleted at the finishing state. So a process, we create a PCB like a file or a card, and every time something happens to the process, we write it. Every time it goes to the CPU, we write what time it went in. Every time it stops, so we keep a record of all its activities. And when eventually it finishes, we take that information, write it into the log, and we delete the PCB. Okay? Right. Next thing, what else is done to a process at the new state? Any idea? We create a PCB for it. Anything else? Anybody remembers anything? Anybody remembers what do we do to a process at the new state? What's created? Any idea? What happens to you? What's given to you when you come into college during registration? That becomes your identifier for the rest of the period of time you're in the college. You have some identifier. They're given an ID. In your case, it's your student number. They give it to you the day you start your registration, and that's going to be used to identify you. So same with the process. Every time you say run this program, it goes into the first thing they give it an ID inside, internal ID. While it's executing, it has this number. So if we say interrupt this program, we don't interrupt the wrong program. There's an ID that identifies only one program. All right, and what else happens to it? We create a new PCB. You need to remember these things. Take them logically, or tell them in a story, or do whatever you like, but you need to remember. What happens to a program in a new process? We create a PCB. It's given an ID. It's given a priority. Normally, the priority depends on the user who submitted that process, and so on. Right? And then it's also classified. The system finds out, are you a CPU bound or IO bound? The system needs to know. It also, in many systems, they say, what do you need to run? What files do you need? And it gets the list of those files that it needs. It's required. Because it might need a scanner, we don't have it, so we can terminate it now. If it needs. So we see what requirements it needs, what devices or what, in this case here, what files. And then once all that is ready, it's put into the ready queue. Say, go, you can run now. Of course, it's not sent to the CPU. It's sent to another state. The state now you're no longer a new, you're already running into the system. Go into the ready queue or ready state. What's the ready queue? What does it do? What does a process do at the ready queue? Any hands up? Is it running? Is it doing something? It's waiting for the CPU to become ready. If the CPU is available, so it's doing nothing in the ready state. It's just sitting in a queue. It's not even awake, it's asleep. Doesn't even know it's there. But it's doing nothing, and nothing happens to it. Until the CPU is ready, and then it will be moved to the CPU, to the running state. And what happens at the running state? First, all the information of the last run are uploaded. We do context switching. The one that was using the CPU goes out, we read that information and put it into its PCB, but this one we open its PCB, we say, what do you want? How far did we, which line number have we started? If it's just still at line number 1, that means that's the first line we're going to be using. So this is where context switching happens. The CPU information is written for the outgoing process, that's the leading the CPU. But the new one, the next one coming from the ready queue, we take its information, put it in the CPU. That's called context switching. So context switching happens at the ready queue. And now at the ready process, the running process. And now the CPU starts running the lines of this process, execute. That's the only time the process is really, something is happening with the CPU. It's running at this point. Keeps running, all the instructions, keeps going until it gets to an instruction that says, hey, I need input or output. I need to read something. Then the interrupt is done, the process puts sleep, and context switching happens. We bring another one, and this one comes out, and the process scheduler will put it into the correct queue. You're waiting to print something on a printer or a floppy disk or read or get the sound of a microphone or whatever. All input-output devices. Each one of them has a queue, so we put in the right queue. So what happens to a process here? Nothing. The process is asleep again. But its input or output, it's done on its behalf. The request, for example, while it's at the CPU, is requested print 3 pages to the printer or display this on the screen. So start displaying. And then when that job is finished, what happens when the input or output for a process is done? What happens to a process here? If we finish the locked state, we've done the input or the output. Where do you think the process will go? Where? Where do you think the process will go from the locked state when it finishes doing its input or output? Any idea? It goes back to the ready state, into the ready queue. So I put it in the ready queue. So when it finishes doing whatever it's supposed to do, well, it was done on its behalf, obviously, the process doesn't do it. No process or program is allowed to deal directly with any of these devices. You can't say, no, I'll do the running myself, I'll print myself. No, you're not allowed. You issue the command, you put to sleep. That happens there at the CPU. You put to sleep, we go and print on your behalf, and you don't know what it's happened, but then when it's done, we move you back into the ready queue. You're still asleep. You'll only wake up when you're back in the CPU at the next line. And you think you just did print and sprint. It could have taken a long time, but you're asleep. When you say print, you put sleep. We move you around, you go print, it might take 10 minutes of printing. Move you back to the ready queue, you might spend another 10 seconds in the ready queue. And then we move you to CPU, you're on at the next line. Printing is done. And you say, okay, you don't even, like the process doesn't even know. Of course, you will know if you want, you can say, okay, what time, you can, in your code, if you want to know how long it will take, in your program, you put the line before saying print, you can say, print, show me the time now, or hold the time, read the time and save it for me, and then request a print, and when you come back again after the print line, say, show me the time, and you'll see how long it actually took. But without that, you don't know. It's like a patient going into an operation, they're put to sleep. They don't know whether they spent 10 minutes or 10 hours, they don't know. They just wake up and whatever the operation is done, oh, they fixed my finger, oh, great. It could have taken 10 hours. But same as here, we don't know how long it took unless if you decide you want to take the time and store it as part of the running of the program. Okay, so transition from one state to another is initiated by either of the schedulers, either the job scheduler for the higher ones or the process scheduler. So the job scheduler looks after the first state, the new state or the holding state, so it moves stuff from the hold to the ready. It also moves stuff at the very ending state. So those two states. So moving a job, who moves the job from here to there? That's the higher level scheduler. And who moves the job from here to there? The high level scheduler. The low level scheduler moves it from ready to the running, to the block, to the ready, to the running, back to the ready. This is all done by the low level, the detailed one, the one that organizes CPU and I/O devices. The other part is just a high level, doesn't deal really with the details. Collects information at the start and picks the information and stores it at the end. Process control block, a PCB. What is it? Where is it going? How much of its processing has been completed? And where it's stored? And how much it has spent in using resources. That's all that information is on the PCB. The PCB normally will have at least the following information. Process ID. So you're given an ID. The program is identified once it goes into the system. Process status, the status, and the process state, which state are you at? Are you at the new state or the terminating state or ready state? And some accounting information, like time accounting, how much time, what time did you come in, what time did you leave, what time did you use the CPU, what's the total time CPU used for? How long did you use I/O? How long did you spend in the ready queue waiting for a CPU? It has a pointer as well that points to the address of the actual process. Remember, the code is in memory somewhere. So it tells you where my code is, for example. And the state, am I in new state, ready state, running state? identifying number. So these are the kind of information and each one of them, what it means. And if you have opened files, what files have you opened? And if you are reading from files, which record have you read, the last record? So if you say read another record, we know exactly. If you've opened a file, you read up to record 16. So when you come back again and you say read the next record, we know it's number 17. So these are the kind of information that are kept in the PCB. And this is the information that needs to be uploaded into the registers, into the CPU for the coming process, and we take out and save the ones for the process leaving the CPU. That's called context switching. Okay, let me ask you another question. So this is the kind of information you see in the PCB. You can look at it later. But I want to ask a question here. Let's go back to this one. What will cause a program or a process, to leave one state and go into the next? What will make a process go from ready to running state? Any idea? Why would a process go from the the ready to the running? When does a process go from the ready to the running? Any idea? Once the CPU becomes free, available, and that process is the next one in line. So remember, there are few processes running here, waiting, and there's a process running in the CPU. When this process leaves, the CPU is free, then the next process in line should be moved. So the process, and how is the process moved? Does it move by itself, or who moves the process? Who actually moves the process?
Job scheduler.
The job scheduler, or the high-level scheduler. Remember, a job never moves by itself. The movers are the schedulers. But remember, we have two schedulers. One scheduler over this line that takes care of those two, moving from here. Well, I don't know if it just takes care of those two. But the one that moves is the one that we're starting from. When does a job move from running to blocked state? When does a job move from the running state to the blocked state? Anybody ready with an answer?
When it's waiting for an IO.
When it requires an IO. When it says, I need to read or produce this output. Then it's sent, and now it's waiting there. When it goes there, it's waiting for it to be done. But here, that's what causes it to be moved. To be moved from running to there, if it says, I need input, I need to read something, or I need to write something. Then you say, well, hold on, you can't do it here. Move it there. Now it stays there, waiting for that thing to be read or printed. Right. When does a process, at the end there, move from the running state to the ready state? From here to there. So it doesn't need input or output, but it's moved from running to ready. Why?
It is interrupted. It is interrupted.
Okay. Yeah, interrupted by who, or why would it be interrupted?
Maybe it is asking for any input or output.
No, the question was for you. Anyway. Okay. Why would a process be moved from the running to the ready? It doesn't need any input or output. Any idea? Pardon?
And it's more time than the quantum time.
If it exceeds the quantum, if it's using the CPU, it doesn't want to leave the CPU, doesn't need input or output. It just continues using the CPU, but we have a quantum. If this system uses quantum, they say, okay, that's enough, that's too long. We move you back to the ready queue, and we give the CPU to another process. So it's forced, it's interrupted to be moved. We take the CPU away from it if it doesn't give it up by itself. All right. And why would a process leave? Give me another reason why. Now let me start the question new again. A process is in the running state, and one moment after that it's not in the running state. Give me reasons why. Why a process is in running using the CPU and suddenly it's no longer using the CPU. Any idea?
No priority function.
Okay. No priority function, we haven't talked about that. Yeah, anything else? Yeah?
The program has an error.
If the program has an error, what happens to it? Does it go to the blocked state or the ready state? If the program is running here, it develops an error. Is it sent to the blocked or the ready state? Pardon? It's sent to the ending state or terminating state. Yeah, so that's the second reason. So, okay, what was the first reason? Why would the process leave the running state? Give me one reason. If it's finished normally, okay, so if it commits an error, it finishes and it's sent there. If it finishes normally without error, it's also sent to the ending state. So, okay, I'm going to start counting again. These are the two reasons why a process is no longer in the ready state. If it finishes normally or if it commits an error. Anything else? Why would the process leave the ready state? Yeah? If it says I need input or output, well, that's reason number 3. If a process says I need input or output, it will be taken out and put in the waiting state or the blocked state for the input or output to be done. If it finishes normally, if it commits an error, it's terminated. So these are 3 reasons. Another reason why a process leaves the CPU, the ready state. Come on guys, this line has been quiet for a while. If it's already in the running state, it has the CPU, and then suddenly it doesn't have it anymore. Where could it have gone? What could have happened? We said it could have finished normally, we moved it to the terminating state, or committed an error, we moved it to terminating state, or it says I need I/O, we moved it to the blocked state. Where else could it could go? It could go straight to the ready state. Why would it go from the ready running to the ready? If it exceeds the quantum, not the quantum itself, it's exceeding the quantum. All right, so these are at least 4 reasons why a CPU, a process that has the CPU running, after one moment it's no longer running. It could have gone to the ending state by finishing or by committing an error, or it could have gone into the blocked state by requesting input or output, or it could have been moved to the ready state, interrupted and moved to the ready state because it exceeded the quantum. Anybody knows any errors that can cause terminating a running state?
Incomplete data.
What?
Incomplete data.
Oh, no.
Didn't hear.
Incomplete data.
Incompleted.
Data. There's not enough data.
The operating system will not terminate a process before it asks for data. The data wasn't there. It might push to sleep until the data is provided. So somebody here said, what is it? Not out memory, but if a process tries to access memory that it doesn't belong to it, that's an error, termination. It cannot access someone else's memory. So if that happens, you're terminated. Any other reason for termination? Anybody knows why a program might be terminated? Yeah? I saw the hand going up and down. Okay, have you ever written a program and got terminated? Overflow. Overflow Is it, for example, you say, I have an array of 10 items, read me the first item, read the second item, third, and then you say, read me the 11th item. There's no 11th item, so that's overflow. If you try to reach another place in memory, basically, that even if it doesn't belong to someone else, even if it belongs to you, but you didn't tell us about it. You just told us you have an array of 3 numbers, and you try to read the 4th number. That's another error. Or anything else, a division by 0 is not allowed in computing. So if your program will say divide x divided by y, but you have 0 in y, then that's division by 0. That's also another termination. Your program will terminate. So these are examples of why a process might lose the CPU or give up the CPU. Any questions, guys? So next, on Friday, we'll study the scheduling policies. What are, if the CPU is available and there are 10 processes, which one would you give the CPU to? That's called the policy. We decide the policy on that. Or we look at the policies that are involved. Okay, as anybody has a problem with attendance? If your name is not, if you're not getting your, hold on, let me, I should have stopped recording before this.